Sorry for the delay. There's some issue with this recording settings. Okay. Okay. Welcome everyone to week 7 of this PMRF TA sessions for the NPTEL course Electronic Properties of the Materials Computational Approach. A brief introduction of mine. I am Akshay. I am a PhD student PMRF in the Solid State and Structure Chemistry Unit SSCU of the Indian Institute of Science, IISc Bengaluru, India. I did my BTech MTech dual degree from IIT Kanpur in the Department of Material Science and Engineering, and I am an NPTEL PMRF TA for this course. And because of some unavoidable reasons, we are having we were having on every Friday, but today we are having this session on a Saturday. Alright. So in today's session, what we are going to do is we are going to start with from in the previous session we were doing some we were completing the coding problem. So we will go through again this week 3 lecture codes. Alright, we will go through week 3 lecture codes, and then we will solve some of the coding assignment problems, and then we will solve some problems on the Brilliant Zone and Fermi surface calculation, and also there will be a and one more numerical problem, and then if time permits we will try to go through the assignment solution of week 5 and week 6. Alright, so let's just so let me just go to Alright, so in the last session, so I was doing this week 3 course, because in week 3 these lectures were done for the 3D gas mostly, so we were done with those 4 parts. So in this session we will just complete the rest of the things, which is we have to the codes for the plotting energy times the Fermi function times the density of states for T approximately 0 Kelvin and T greater than 0 Kelvin, and then we will calculate the total energy for T greater than 0 Kelvin. Just a minute if I might be okay. 1 minute, let me just actually my health is not today that well, so I might be a little slow. Okay, so basically so first we will complete this plot. Okay, we have to do the check the codes for the plot of energy times the Fermi function times the density of states. So this we have done in the previous session. All this discussion was done, and we have done the analytical calculation for N naught as well, and I have shown you both type of codes. Then we have to do numerical scheme to calculate mu. Okay, that will be afterwards. Okay, yeah. So we can do part 5 and 6 first, and then for 7th we will do some discussion as well. Let me just stop sharing from this one. Let me just start sharing here. Lecture codes. Alright, so we will start with this week 3 lecture course, and we will start with our code number 5, which was remaining. So let me go to code number 5. This code number 7. Okay. So the code number 5, in code number 5 we are basically we are plotting the 3D plot for the energy times the Fermi function times the density of states at T approximately 0 and T greater than 0 Kelvin, right? So first you have to import, first again we are just importing these libraries. KBT naught we have taken, instead of 0 we have taken a very small value. KBT, it is around room temperature, you are taking 25 milli electron volt. Fermi energy we are taking to be 1. This is our beta naught, which is 1 by kBT naught, and then we have beta equals to 1 by kBT. Then we have this NP tolerance with numpy array that we are getting from 0 to 1.5 times of EF, and these are the Fermi function at Fe naught and Fe. Then this is our density of state for the 3D case. As you know, it goes by square root of E. And then here we are just plotting these values. We are plotting these energy times the Fe naught value for t approximately 0 and then for t greater than 0. So if we run this code, alright, so here we can see that, okay, so this is what we got for the energy times the Fermi function times the density of states. Here we can see that again the same thing, like this this is the Fermi energy. Okay, let me just get that Fermi energy line as well. Alright, so here as you can see at the Fermi energy, as we know, near the Fermi energy mostly the t greater than 0 and t approximately 0, these curves generally change around in this area only. Alright, and for t less than 0 we just have the Fermi function is just 1, while there will be difference for t greater than 0 because Fermi function will change around the Fermi energy. Now for 2D and 1D, as we have done earlier, for 2D case you just have to change your density of states in the code. So code number 5, the 2D case. Alright, yeah. So this is the in the 2D case again we are doing the same. You can go like I have taken like 0.001 as well. You can take a small value or something, and all the rest of the things are just the same. You just have to change because for 2D it is just a constant. So I have taken np.1 2000 float. So you can just take this. You just have to change the density of states in the code here. Okay, and here again for the 2D case as well we are getting something similar, although you can see that this is basically the straight, we are getting a complete straight line here because the the density of state is basically just a constant, okay, and we have taken the constant to be 1. Alright, so and again we are still seeing the change around the Fermi energy only. So you can check from this code the difference. You will see like the curvature is a little different 2D case, and if you have to do it for the 1D case, and so we will go to the 1D codes and this code number 5, number 6, alright. Now for the 1D case, just remember that for 1D case it is 1 by square root of E your density of state. So energy value we start not from 0, like the energy density we have to do 0.001, and then again just change the density of state, which is 1 by np dot square root of E. Alright, and the rest of the code is just the same. Okay, rest of the code that remains the same. You just have to change the density of states, and this is what you will get for the 1D case. Alright, because of 1 by square root of E, it will look something like this. And again you can see the difference for 1D as well, between t approximately 0, t greater than 0, it is around the Fermi energy. Alright, okay, so let's go to the next part. Let me stop sharing this one, and let me go back, see about that. Start sharing. Okay, we have done this code. Alright, so this part is also done. Alright, and okay, I was 10 minutes late. It's 3:23, right? We are recording my 10 minutes. Alright. Okay. So okay, now then the next part is to calculate the total energy at t greater than 0. Okay, so now we will do this coding part, and then we will go to the seventh code. Now we have to calculate the total energy. Stop sharing. Just alright. So okay, and let's go to the code number 6, which is our energy, total energy calculation. Again, 6. Alright, so we have to calculate total energy. So for this, what we are doing is we have taken different calculating total energy for T greater than 0 for different range of temperatures. So this is the range of temperature that you have taken, and NP dot space you have taken from a very small 0 value to room temperature now 25 milli electron volt, and we have divided it into 50 points, 50 temperatures along this range, and they have taken delta E range D values, which is the D intervals in which we will calculate, so that we have taken to be NP dot 50 NP dot 50 of this numpy array. Now for calculating the total energy at approximately 0, we have B naught, we have our energy F naught. That is basically we have to take the plot that we have done in the previous code, which is the energy times the Fermi function times the GE. So you just have to take the integral, and that will give you the total energy, and this is for T approximately 0 what we are taking. And then for calculating total energy at T greater than 0, what we are doing is we are again doing the integration for taking the Fermi function with the from this one Fe, instead of 1 by kBT we are taking for each of the kBTI temperature, and then we are integrating those curves that we saw in the previous code. You just have to integrate them, and here E and T gives you the total energy, and D is basically the difference between the total energy for T greater than 0 and the energy at T equals to 0. Alright, and then we are just plotting this, and then we are just plotting this energy difference, okay, for between the total energy that has been calculated at some temperature T greater than 0, which is E and T, minus E and naught, which is at T approximately 0 we have taken. Alright, so let's run this code. And density of states, since it's a 3D, we have NP dot square root of E, and I have also drawn a kBT square, so you can see that this delta E, which is the delta E energy difference with respect to kBT square, it goes as a straight line. So our change in this energy, it goes as kBT square, as you have seen in the lecture as well. Alright, and now to do it in 2D and 1D is the same thing, and let's go there. Alright, now for the 2D case you don't so for the 2D case it is same. Okay, you have to you just have to change your density of states as earlier. You just have to change this to NP dot ones. Okay, you have to we are just, because for a 2D case the density of states is just a constant, you just have to put that, and NP dot okay, yeah, so I don't know how it's happened. Right. Yeah, so you just have to change the density of states in your code, and let's just see how it goes like with kBT square something. And for the 2D case, yeah, for the 2D case also it goes somehow similar to this KBT square. You can see, although you can check the slope length how it is increasing or decreasing later on. Okay, so yeah, so all you have to do is you just have to change this density of states. And let's go to the 1D part quickly. And for the 1D part, again the same thing. Okay, just remember that for the 1D don't start the energy SKBT value from energy value from 0. You have to take from 0.01 something like here. Okay, and again the density 1 by np dot square root of E. Right, so that's the same. You just have to change the density of states here. Alright, for both of them I have changed it. Right, let me just run this code. And for 1D also we can see that okay, it goes like this. Alright, but you can see the increase is you can see this values delta E is those values will be a little different. But in both the three cases we have seen that basically with KBT square this change in this energy will increase. Alright, alright, so let's stop sharing. Alright, so now the last part. Alright, okay. So let's go to the last part, which is to calculate mu at t greater than 0. For this, let's just revise a little bit for a small theory, like what is a numerical scheme to calculate mu at t greater than 0. So at t greater than 0, we know that okay, so we can find the total number of electrons and as a function of t comma nu by this integration. What we were doing, like the density of states time the Fermi function e to the beta epsilon minus nu plus 1 t epsilon, that will be a total number of electrons. Beta is 1 by kVt. Now to calculate mu, we assume that n naught is equals to n at any t, which is the constant volume. If you are considering constant volume process, so we can assume n naught is equals to n, and n naught calculation, for n naught you just have to do your Fermi function. We know that it will be just 1 for up to Fermi energy. So n naught is easy, we have calculated in the previous session as well. We have seen the analytical and both the coding part. Now for a given t, n depends on the value. So for a given t, we can see that the n depends on the value of mu. So the algorithm was at a given t, start with a guess value of mu. Okay, so for at a given t, we will start with a guess value of mu and tune it until you get n equals to n naught. Okay, so we will start with a guess value of mu and we keep tuning it until we get n equals to n naught. Alright, so that is the algorithm behind this, and so this is the code that we will do now, and then we will do our problem as well. Okay, let me just start sharing. Alright, so let's go directly to so this is for calculating mu at different temperatures. This is the temperature range that we have taken. This is the mu values that we are storing, and this is the Fermi energy. Here we have taken 2.5. Alright, and n naught, as I have shown earlier, either you can do the integration under the curve. Okay, we have seen like this, or for the 3D case we have derived, like for the 3D, 2D and 1D, we have derived this analytical expression as well, and we have checked it for both 3D, 2D and 1D, that either you can use this analytical expression for n naught, which is basically the number of electrons at T0 Kelvin, or you can do the integration under the curve. Okay, so both gives the same results. This we have checked in the previous session. Okay, so then you have this function. What this function does is it takes these energy values, the Fermi energy, and gives you this integral, which is your n values. Okay, so that gives you your n value. We can do this integral. Okay, and then we will start with our mu. Now mu, we know that it is mu is around the Fermi energy. Okay, so even at like generally we have seen in the lecture, as we discussed, mu doesn't change much compared to the Fermi energy for the temperature range that you generally work, even around room temperature. So our first initial guess will be for mu will be for we will take as the Fermi energy. Then what you can do is then we will run it for all the temperatures. We need to calculate mu. Here you are taking beta, then you take your NT should your number total should be just whatever n naught plus, we know it will increase, so n naught plus 0.5, this is your guess. Now while this NT minus n naught is very small, because of our approximation, our algorithm is, as you remember, our algorithm is we have to go to we will continue, we will keep changing this mu until we have at a given t start with a guess value of mu and tune it until you get n equals to n naught. So we have taken basically we have taken this threshold criteria, like the difference, there will be some difference. We are saying that it should be like less than 10 to the minus 5, 1, 2, 3, 4, 5, 6, minus 6 or something. Alright, so while this is, if this difference greater than this, then what we are getting, we are just reducing our mu by a very small value, and then we are again calculating our NT, okay, total number of electrons at that temperature, and then we are just seeing that basically that just gives you until we have NT equals n naught, we are just decreasing our Fermi energy, because our Fermi energy must be decreasing, and then only we can this mu must be decreasing, it must be becoming less than the Fermi energy. Alright, so we are updating it here, and then if we reach this value, then we just put that as our mu value, whatever whichever mu satisfies this while loop criteria at the end. Alright, and this is just the plot, and we have there are two plots, mu versus epsilon of f as a 3D with respect to kBt square, and then with respect to kBt by EF. Okay, so let us see it. Alright, so we can see that mu by EF with respect to kBt square. So our this mu value will keep decreasing as we increase the temperature initially, and this is how we are updating as well, because okay, so our mu will keep decreasing, but you can see that even the difference is like the mu by EF, it is around 1, it is going up to even at like for kBt square value 0.06, it is like 0.993 only, so the difference is not much. And with respect to kBt by EF also, you can see that the plots look something like this. Alright, so we can see that it almost remains same for this range, and then it starts decreasing. Right, so still the mu most of the cases it is very close to the Fermi energy only. Then let us go directly to the 1D case. For the 2D case, the code runs quite wrong or something. There was some issue I couldn't solve. Okay, but for the 1D case, because that is the coding problem as well, so let us go to the 1D case. And in the 1D case, again, you just have to change your density of states. Basically, you have to change to 1 by NP or square root of E. Alright, and nothing else you have to change, just the for the integration of energy as well. And since your density of state is 1 by NP or square root of E, the energy range should start from a very small value, not from 0, for which you are doing the integration and all. Alright, and then the plots are mostly they are similar. Alright, this is run, and this is what we are getting. Okay, so in this case, remember that for 1D case, what happens is that for 1D we have to actually increase the mu value. So that's the difference between 1D and 3D. For the 1D case, the mu value will increase with the increase of the temperature. Okay, it has to go actually like this. You can check the code. You can, but only increasing only we are getting this thing. So the Fermi energy, our chemical potential will increase as we increase the temperature, and will go something like this. All right. Although again the difference is not that high, kVt by EF for this range it is mostly same. Although later on at high temperature starts increasing, but it will increase. While in 1D, in 3D it decreases, while in 1D it increases. All right. Let me just stop sharing and let me just go to our coding problems now. All right. Alright, so we are done with our this previous session stuff. Alright, so we are done with this week 3 lecture codes. Now we go to our first problem of this session, which is the week 3 assignment coding problem 1. Alright, so in that coding problem, what you have to do is you have to write a code mu-t for the 1D free electron gas and choose the correct option. So this we have right now, we just saw it in our lecture 3 code as well. So what we have seen is nu does not depend on T. That was not the case. We saw that nu decreases with T. No, we actually saw that it increases. Now nu first increases with T up to some temperature and then decreases. No, it actually increases with T. So this is how, that's why our answer is T. Okay, so and this is the same code. Alright, and we can run it again, but you can just check. Okay, this is the same code that we just saw. Okay, so nu increases with T that we have shown, that we have seen here. So I will not go through this code again, or maybe let's see if there is something else. This thing that I have to discuss. Okay, there was just one problem only. Okay, so it was this problem only. Okay, so it's the same code. Yeah, so it's the same code. Sorry, I just repeated it, but basically, yeah, the new value, it will increase with temperature T. Okay, and here we have, like, as you remember, here we are changing this, and we have to actually increase. We can try the minus value. You can try to do it negative as well. You can try to decrease it, but the code will just keep running, and most like, and you won't be able to actually get this condition NT minus n. Right. So as you can see, the code will just keeps running. I have to interrupt it. So the reason was we have to actually increase it. While in 3D it was decreasing. The mu value will decrease with the increase in temperature. So that's the difference between 3D and 3-dimensional free electron gas and the 1-dimensional free electron gas case. Right. Okay, and let me just stop sharing. That is some question. Okay, so let's go to the next problem. Okay, now the next coding problem, it is from week 4, assignment coding problem 1. Now you have to write the Fourier series expansion of the periodic potential using the code shown in the lecture. Find out which of the following wave vectors you can include in the expansion. A is the spacing between two adjacent direct lattice points. Okay, so so this is the code that we are going to use to solve this problem. So what we are doing here, we are going to first import the two libraries. Then if you remember, so basically what you have to do is, in this case it is asking us Fourier series expansion for your potential. We can do it like this, like 2 sometimes summation over k for greater than 0 uk time cos kx, where k is our the k values that we are taking. Okay, generally we know that this case they will be a reciprocal lattice vector, if you remember your theory from the lecture code. So from that also actually you can just try out. Okay, if it is 8, it is like 2 pi by a, and then the other reciprocal lattice vector will be this 8 pi by and 10 pi by a. Other options won't work, but you can check. But instead we can do it with the coding part as well. So what in this code I have written is, you have a lattice parameter a, then you have your k parameter. We are taking pi by a. Okay, we are taking this is the parameters. So our the around k points, as you remember, they will be this multiples of pi by a. Then in this you number of terms sum is taken. Okay, so you just define the number of terms for summation taken. So like for some we are just taking 1, for some we are taking 2. Then this ug and k, these are the list in which I am storing the values and the capital K values. So for now assume ug goes as, and ug we are considering just goes as 1 minus 1 by g square. So then in this coding in this part, in this for loop, I am just appending this minus 1 upon I plus 1 whole square. So that is I am considering my ug. As we know, like in the lecture, it goes like 1 minus 1 by g square, or we are considering here as some number k square, number square. Then then in this part, using this part, basically we are going to enter whatever the key points are given to us. All right, so so basically like all the key points, they are given in terms of this pi by a. So you just have to enter your numerator of your numerator of the key point and the denominator of the key point. Okay, so this is the 2 lines of code which we are mainly going to use to solve this problem. So like for example, for the first part, I will put numerator as 2 and the denominator as 1 to check if 2 pi by a is the finite wave vector we can include in the expansion 2 pi by a or not. Alright, and then nk num, then what it does, this code does is, you take this 2 and this k num does is, I do that is numerator by where denominator will be my k num, and then my k dot append will be k num times k parameter, which is pi by a. Alright, then we take the ug values, then this is the we are just make them an arrays, and then what you have to do is, you have your this is where we store our potential. All right, and then I write my potential as this expansion 2 times this whatever my coefficient is times this cos kix. Okay, so this is how I write the u potential. Then these are the positions for the atomic positions on the x-axis, and then what we just have to check is the potential that I have expanded in terms of whatever the key point I am using, is it periodic or not. Okay, so we will just plot it and see if that potential has the periodicity of this lattice or not. If it has, then that k point, then that wave vector could be used in the then we can use that wave vector in our expansion, otherwise we cannot. Alright, let me just stop sharing. And let me just start sharing the coding problem. So let's just see this code in action, and then I guess it will be much more clear. Alright, okay, sorry, the coding problem, code for, Okay, so this is for the periodic potential considering sum over G. So this is what you might have seen in the lecture. Alright, so in the lecture, okay, so I have included this code here. So this is just for your lecture, week 4 lecture code. So this I will not go through this. These are just week 4 lecture code. So the code that we are going to use is written using these two codes only, like doing some changes. You can go through them, and as you know that if we have this G vector, then we should get something like this. Okay, so if it has the periodicity, it should look something like this. Otherwise, if it doesn't have the periodicity, then it will not, like this potential will not have the periodicity like this. Right, so these are the lecture codes. You can this course will be shared in the Google Drive, so you can check out these codes, play along with them. Alright, so let's quickly do this problem. So in this problem, okay, so the problem that was given to us, we have now, this is the same code that I discussed right now. So here I am putting the k values, and then I'm doing this extension, and then we just have to plot, okay, and check if that thing works. Alright, so for the first option, so let's just run this code. So okay, now for the part A, so first option is 2 pi by a. We have to check if 2 pi by a can do the expansion. So number of terms, I'm just taking 1. Numerator for me is 2, denominator is 1, and let's see. Alright, so this is my expansion, this is my potential. These red dots, they represent my atoms, and as we know that the potential should be negative at this point, and it should be periodic, and I can see that is happening here. So 2 pi by a wave vector I can include in my expansion. Alright, now let's just run this code again. Now for the B part, we have to check for 5, we have 2 terms, okay, so I will take 2 terms. Now for the first term, I have to take 5 pi upon 5a, so let's just go with 5, and the denominator is also 5. Then for the next, I have to take 3 pi upon 5a, which is 3, and which is 5. Okay, just enter the values, and here you can see that okay, this is not periodic, okay, like it is negative for the at this x equals to 0 point, but otherwise it is like positive for some atoms, and it's not periodic at all. So B option will be wrong for that week for assignment coding problem 1. So B option will be wrong. Then for C option, you will have 8 pi by a and 10 pi by a. Again, I will have 2 terms, and first term is 8 pi by a, so numerator is 8, denominator is 1, and next is 10 pi by a, so numerator is 10, denominator is 1, and this. Okay, so this is the kind of plot that you will get. So it looks little like you might say the C option, or the C option could be correct, but you can see that first of all the potential is negative at each of these red points. Alright, so the potential is negative, and it is periodic as well. You can see that the potential is actually periodic within this within each of the lattice point, and it is negative at the atomic positions. So yes, this is the potential is periodic, and it has a periodicity of the lattice. So yes, with the C option, 8 pi by and 10 pi by, that is also a correct answer. Those wave vectors could also be used in the expansion. Right, and the last option, again we were given 2 k points. One is 2 pi by, again our same 2 pi by, numerator is 2, denominator 1, and then 3 pi by, numerator 3, denominator 1. Alright, and that doesn't give a good answer. Okay, it is negative for all of the atoms, but then again it is not the periodic. Okay, it doesn't seem periodic, although there is some periodicity, but it is not the periodicity of our lattice. So D option is also wrong. Right, let me just stop sharing this. Alright, so we have seen that D option didn't work for us, B option didn't work for us, A worked quite well, and C we saw like there was many lines between each of the lattice point, but at each of the lattice point the potential was negative and it was periodic as well, so C option is also correct. That's why answer should be A and C. Alright, so you can just go through this code and play along with it, maybe some other key points as well. Alright, so let's quickly go to problem number 3. Alright, so the problem number 3, it is the week for assignment coding problem number 2. So what you have to do, you have to write the Fourier series expansion of the block function, okay, psi of x, your wave block function, using the code shown in the lecture. Again, find out which of the following wave vectors you can include in the expansion. Assume length of the solid is given 10a, where a is the spacing between two adjacent direct lattice points. Alright, so the correct expansion of psi x must now for this we should remember that the correct expansion of psi x, it has to satisfy the following criteria. One is this, the probability distribution factor psi of x plus na whole square should be equal to psi of x square. So basically your probability density should have the periodicity of your direct lattice, and then you have to satisfy this periodicity as well, like psi of x plus na, the periodic boundary condition. So this comes from the block condition, and this comes from the periodic boundary condition. Okay, periodic boundary condition. Alright. Psi of x plus capital N is equal to psi, where a is the spacing between two adjacent lattice points, and a is the length of the solid, and n is just an integer, small n. So, and in our problem, capital N is given to us as 10, and this a lattice parameter we are just taking it to be 1. Alright. So to check if whichever key points will be there, this is the code. Okay. So first again you have to import your libraries numpy and matplotlib. Now taking up to we are just taking up to 2 terms, so we can do this expansion. This is from the lecture, ck1 times e to the power eta k1x plus ck2 plus times e to the power eta k2x. Alright, a we are taking as 1, capital N we are taking as 10. Let me just okay, and then this is our parameter pi by a, whatever we are taking, they are the units of pi by a, right? Then you have to take C1, enter the coefficient. We are just since nothing is set told us and we have to take 2, we are just going to take 0.5 this to be okay. So both coefficient key point coefficient we can keep the same. That doesn't change your answer, that is just for the plotting purpose. Alright, and then this is just like in the same in the lecture codes. Then again from here again, so these are again the 2 lines where we put our these key points, numerator and denominator just have to put, and here then we will have our key points there. Then these are the real part of your wave block function and the imaginary part of your block function. Alright, and then these are just the atomic positions that we have taken. So we will just then we will just plot this wave functions, and we will see if those 2 conditions that we discussed, like okay, so we will plot the probability density. We are plotting the probability density as this. Okay, this is the psi square. Okay, mod of psi real square plus imaginary part square. So we are plotting the psi square. So what we needed, the psi square should have the probability of your your direct lattice points, x plus na should be equal to mod of psi x square, and then your psi wave function, that should be basically periodic. So your basically both your real and the imaginary wave function, they should be continuous at the periodic boundary positions. Alright, so this is the code. Let's just see this code in action. Stop sharing. Alright, and again So the code that I have written, that is based on the week 4 lecture code. So this you can go through yourself, and as you remember, it was summation over G that has worked. So you can just go through this from the lecture code. But the thing that I've changed for this problem, I have just changed this lecture code and then solve this problem, right? And as in the lecture code, if you remember, the so this is not the correct answer basically, like maybe I guess this shows the correct answer. Okay, so we want something like this. Okay, we want this to be a continuous function. Okay, like the imaginary part and the real part, they should be continuous, and we should have a periodicity of this, right? So let us check it for our problem. Okay, so in our problem, what we are doing, we are just putting the key values here. Okay, we are just giving it whatever the key values is. It is doing this expansion, which is just c1 times it. For the real part, it will be e to the power iota kx plus k2x. It will be cos of kx and c2 times np dot whatever the cos function of kx, k2x, and the imaginary part will be for the sine functions, right? Alright, and we'll just do it for our problem. Alright, and capital N, I have taken it to be, you can see, okay, we have taken capital N to be 10 as asked, right? Let's just run this code quickly. Coefficient just take 0.5. Alright, now for the first key point. Alright, for our option A was 4 pi upon 5a and minus 6 pi upon 5a. Alright, so numerator is 4, denominator is 5. Now for the second point, numerator is minus 6, denominator is 5. Let's see what we are going to get. Alright, so here just a minute, there's an issue. Alright, I'm behind by 12 minutes. Okay, yeah, sorry about that. Okay, let us start it again. Okay, it was actually correct. I guess. Okay, so let us take 0.5. Okay, the A option is first 4 pi upon 5a, so the numerator is 4, first point, denominator is 5, it is 10 to 5, then numerator is minus 6 and denominator 5. Alright, and okay, right. Now we have to define the two condition. So first we can see that okay, the second condition, which comes from the periodic boundary condition, that these wave functions, they should be same for x psi of x plus capital Na. These are the 10 points. Okay, you can count 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is the total length of our system. This is total number of points, which is 10a. So blue curve, that you can see that this periodic boundary condition is being satisfied here. Okay, from 0 to 10. Okay, the blue curve is here and it is continuous, and the green values, it will also be continuous. Alright, so that condition, periodic boundary condition, is satisfied, and we can see that our periodic our mod of psi square, that is also, it also has the periodicity of our direct lattice. So mod of psi of x plus small na whole square, that is equals to mod of psi x square. Right, so option A is doing good. Alright, so option A will be correct. Then let's do the rest of the part. Let me just show you. I guess I can show. So we can see that our option A is correct. Okay, now option B is 4 pi upon 5a and 14 pi upon 5a. So again I will just enter 0.5 here. Okay, now our B option is 4 pi upon 5a and 14 pi upon 5a. So just enter 4 and 5, which is the first key point. Then second is 14 and 5. 14 and 5. Okay. So here we can see that again this continuity is still being satisfied. Here we can see that okay, the blue curve, it is continuous, green curve is also continuous, it's going up and then it will go down, and so, okay, so that continuity, the periodic boundary condition is fine, and the this condition is also satisfied. Okay, so our mod of psi square, it has the periodicity of our direct lattice. Alright, so yes, so B option is also working quite well. So A and B options both are correct. Let's go to our C option. Okay, and again just put 0.5 here. Alright, for C option, our point of 4 pi upon 5a and 5 pi upon 5a. So 4, 5, right, and 5, 5. 5, 5. Just put the values in and see what happens. Now here we can see that again the periodic boundary condition is still being satisfied. Alright, the blue curves, you can see that okay, they are still satisfying the periodic boundary conditions, they are continuous. So psi of x plus capital N is still equals to psi of x, right? But we can derive mod of psi square, it is not periodic at all. So our C option is C option is wrong. C option is incorrect. Now again, let's just take the last option. Just put 0.5. Okay, the D option is 3 pi upon 5a. You can say 3 pi upon 5a and 5 pi upon 5a. So let's go to 3 and 5, 5 and 5. Right. Again, the periodic boundary condition is being satisfied, but we are not seeing this mod of psi square. That block condition is not being satisfied. So so this is not a correct answer. Right. So D option doesn't work. Okay, let me just stop sharing. Alright, so from our code we have seen that part A, this A and B wave vectors, they satisfy all the four options. They are going to satisfy this condition. Periodic boundary condition is being satisfied, but this condition is not being, this first condition, okay, that is on our this mod of psi square, that is being satisfied by option A and B only. It is not being satisfied by option C and D. So our answer will be A and B. Alright, let's go to our next problem. Okay, so we are done with all the coding problems that were left. Alright, if you have any doubt, please ask in the discussion forum. Alright, so in the remaining of the lecture we will do some more problems, some problems on Brillouin zone and Fermi surface, and also a problem, numerical problem as well. Okay, alright, so this problem is from Charles Kittle's book, problem number 1 from chapter 9 of Introduction to Solid State Physics by Charles Kittle. So what we are being asked is, we have to make this for the Brillouin zone of a rectangular lattice. So we have to make a plot of the first two Brillouin zones of a primitive rectangular two-dimensional lattice with axes are given A and B is equals to 3A. Right? Alright, so let us do it. So first let me draw our reciprocal lattice. So first we will draw the reciprocal lattice. So let me draw, let's say this is my gamma point. Okay, take it as 0. Now what we have is we have A is equals to, we have an A and we have a 3A. So in the lecture you have drawn for the square lattice. Now we are going to do it for the rectangular lattice. For rectangular lattice we have to do, so my length along this A axis, that will be, so my next lattice point will be at 2 pi by A, right? So I can draw this here, and then I will have one lattice point here. Okay, let me just keep it same. Okay, so hopefully it is the same. So this will be 2 pi by A comma 0. Okay, this is my reciprocal lattice point, and this is minus 2 pi by A comma 0. Alright, now other ones that we will have, it will be, because B is now 3A, I will have it a little, I will have it closer now. Alright, this will be my lattice point, this will be closer points. Alright, this will be 0 comma 2 pi by 3A, and this will be 0 comma 2 pi by minus 2 pi by 3A. Alright, that is happening because we had a rectangular lattice, so our reciprocal lattice will also be a rectangular one, right? And let me just put all the other points here. Okay, now we have to draw the first Brillouin zone. Now for the first Brillouin zone, so first what we have to do, we will connect this gamma point to our nearest neighbors. Okay, so for the first Brillouin zone, I will connect these 2 points first. Okay, you can start with this, or actually we can see that the nearest points are actually this one. So I will connect these two here. Okay, so this is not exactly same, but just assume that this is same. So the drawing was not that correct. Let me see if I can move these things. What maybe? In that case, let's see. Alright, now let's undo it. Alright, okay, yeah, so now the lattice looks a little okay, I guess, yeah. Alright, so this will be your 2 points, and for the Brillouin zone, what do? We draw the black plane, and that will be the perpendicular bisector to this. So what you can draw this perpendicular bisector here. Alright, now we can connect this to these next nearest neighbors will be this one. You just connect these 2 lines, and then we will do perpendicular bisector. Okay, so the drawing is not that okay. So I guess this also perpendicular bisector. So let me just move this point. Make these things very small. some things if that didn't work. Alright, okay, now let me just draw the perpendicular bisector to this one as well. Something like this. Alright, so this is our black line, black plane basically, which is the perpendicular bisector. Now from 0 to 2 we have connected this 0.2 to pi by point, and again we have to do a perpendicular bisector. So you can do it like this, and similarly I will have a perpendicular bisector here as well, like this. Right. Now for the first brilliant zone we can see that this surface will be the reason, okay, because we already have covered, like if I connect any other lattice point with the gamma, then I will be crossing one of the black planes. So I have to like cross one of these four black planes that I have drawn here. So this region is going to be our first brilliant zone. Okay, so we can go from any point in this region. So I just shaded with this purple color. Right. So this is our first brilliant zone. Right. Or let me just this will be our first brilliant zone. I guess this will be clear. Okay, so this is our first brilliant zone. I'm not shading it completely. Alright, so this is our first brilliant zone. Okay, so this color shows our first brilliant zone. Now for the second brilliant zone, let us just take some lighter color. Okay, now for the second brilliant zone, what we can do is, let's go from 0. So okay, second brilliant zone, we know that we have to cross at least one black plane. So let me just connect the next nearest neighbor. So next nearest neighbor seems to be this one. So first we will connect these two, and if you go, it will go something like this. And then the perpendicular bisector, if you draw, then it will go like this actually. So let me just go like this. Right. Alright. Then we can connect our perpendicular. We can connect our lattice parameter with this one. Okay, next nearest neighbor will be this, and this, and its perpendicular bisector also. So my drawing is not that good, but I hope you can understand that it must go through this line. Alright. Alright. Then again I will have similarly, I will have one point here. Let me just connect it here. Perpendicular bisector, if you will draw to this one, the blue, so this will be the next blue black planes, you can see. Alright, and then you have we can connect this to this point as well, right, and this will go through, this will be your perpendicular bisector. Alright, then we can connect this gamma point to this point as well. So the line will go from here to here actually. Okay, so I'm connecting this point, this blue line point, and this perpendicular bisector will go through this lattice vector. Alright, and similarly you can draw one line from here, okay, to this point, which is 0, you can say 4 pi by 3a, and I will have a black plane here. Okay. Now what we have to do, so let us the 6 lines that I have drawn, so we will just go through this and see if we are cutting a black plane. So what happens is, so we can see that in this region, so our second brilliant zone will be given by this region, which I am drawing with this blue one. Okay, so let me just draw it once. This will be the perpendicular bisectors, and this will be the region enclosed. This might come a little here, but that is just a drawing thing. Okay, so this region, this will be your second Brillouin zone, or here you can see that, okay, so this will be the second Brillouin zone region, and here you can see that each ever point we have to cross. So like I have to reach to some point here, then I have to cross one of these black planes. I have to cross this purple one black planes. All right, and if I go beyond this region, then I will be crossing the blue black planes. So that will go into you, as you remember, that will be your third Brillouin zone. So your second Brillouin zone will be only in this region. So I will just shade it with blue. Alright, because for the blue to reach any of these points from the 0 gamma point to any of this blue region point, you have to cross this purple black planes. You just have to cross one of them. So those regions comes in your blue in your second Brillouin zone. And if you go beyond that, then you have to cross this blue black planes as well, which will actually gives you your third Brillouin zone. So this shaded area, this is your second Brillouin zone. Alright, so for the rectangular system we have drawn both the first Brillouin zone and the second Brillouin zone. Alright, so this was the problem. So I hope drawing Brillouin zone would be much easier. You just have to connect this lattice point through a perpendicular bisector, and then you just have to check while going from within this region, are you cutting any black planes or not. This perpendicular bisector, this will be your black planes. You just have to check how many black planes you are cutting. Alright, so this was problem number 4. Let's go to problem number 5. Alright, so in problem number 5, okay, so in problem number 5, what we this is also from Kittle, problem number 2 of chapter 9 from this Introduction to Solid Space by Charles Kittle. So we again have a problem on the Brillouin zone of the rectangular lattice. So what is given to us is that two-dimensional matter has one atom of valency 1 in a simple rectangular primitive cell A. Okay, so we are giving a primitive cell whose lattice parameters are A is 2 angstrom and B is 4 angstrom. First we have to draw the first Brillouin zone. Alright, let's do this part A. First I have to draw the first Brillouin zone. So again it looks like the same rectangular. So I will make my gamma point. Now this distance is given as along A it is 2 angstrom and along B it is 4 angstrom. Alright, so it will be 2 pi by A. So it is basically like 2 pi by A, and along the B this will be smaller, yeah. Right. Alright, so I will have this this will be 2 pi by A and plus 1. Alright, so first we have to make draw the first Brillouin zone and give its dimension in centimeter inverse. So the Brillouin zone, if we draw it in the same way, again what we again have a two-dimensional matter. So again we are just talking about 2D lattice only. Okay, and we have A is 2 angstrom and B is 2 pi by angstrom. So I can take 0, I can take this 2 pi by A, and next will be 2 pi by 2A. It is because if A is equals to 2 angstrom and B is actually twice. So if I draw this, so it is similar to what we have done in the last problem. So, and I just have to draw the first Brillouin zone. So I will draw it again, and just draw it like this. And and this distance. Okay, so this will be 2 pi by a comma 0, this will be 2 pi by b comma 0, and b is equals to 4 angstrom. B is some like 4 times of 2 times of a. Okay. B is equals to 2 times of a, so that will be that's why this will be a smaller value, right? Okay, similarly what we have done just in the previous case, right? Then again what we have to do is we are just talking about first Brillouin zone, so I will just connect these first two Brillouin zone. This 2 pi by length will be longer. Same two lines. Right. Just do a perpendicular bisector here. Just draw a perpendicular bisector here, just draw a perpendicular bisector here, and this will be our first Brillouin zone. Alright, it is similar to the previous problem. Okay. Now other thing that it is asking us is give its dimension in centimeter inverse. Alright, so if you know that if this is a perpendicular bisector, so this point, this is our Brillouin zone points. Okay, so this is your Brillouin zone, this is your first Brillouin zone. So for this rectangular system, it will be a rectangular. This point will be equals to pi by a comma 0. This point will be equals to pi by b comma 0. Alright, and a value is given to you as here a is given as 2 angstrom, or it is 2 into 10 to the power minus 8 centimeter, and b is given as 4 angstrom, which is 4 into 10 to the power minus 8 centimeter. Okay, so it is just asking us the dimension of this first Brillouin zone in centimeter inverse. Okay, so if we can see that our first Brillouin zone is again a rectangle. Alright, so we will have some length and breadth. Okay, and these are the points. This is pi by b, this is minus pi by a comma 0, and this is 0 comma pi by b, and this point, these are 4 points, and this will be 0 comma minus pi by b. So my length of this side length, this dimension, that is basically 2 pi by, this dimension is basically 2 pi by b. So if you so this basically comes as 2 pi by b dimension, and this length will comes as 2 pi by a. Okay, and if we so if you just do it, the calculation in centimeter, because this will come in centimeter inverse, times pi divided by a, which is 2. So it comes at 3.14 into 10 to the power, because minus 8 centimeter inverse, 10 to the power 8 centimeter inverse. Okay, so this is the dimension of your this, or you can say the pi by a value, this point. If you are talking about the coordinates, so this coordinate, this distance from gamma will be 1.57 into 10 to the power 8 centimeter inverse. But but I guess it is asking us just give its dimensions. So dimensions will be, I guess, will be this length of both of them, which will be 2 pi by a and 2 pi by b, and 2 pi by b will be just half of that, so it will be just 2 times pi divided by b is 4 angstrom, so this will be 1.57 into 10 to the power 8 centimeter inverse. Okay, so these are our dimensions. Alright, so dimensions are of first Spinning zone, it is 3.14 into 10 to the power 8 centimeter inverse along kx, and 1.57 into 10 to the power 8 centimeter inverse along ky. Okay, so that is the length of our first Spinning zone. Alright, so that is only asked here. Then the B part is calculate the radius of the free electron Fermi sphere, that is also in centimeter inverse. Alright, so for that we know that, okay, for the Fermi sphere we know that first we need to find the total number of electrons. We know it, just a quick revision. Okay, so what this comes as pi times kf square divided by 2 pi by, here we have a rectangular lattice, so you have 2 pi by lx times 2 pi by ly, and you have total number of electrons, which will be total number of electrons per unit area, that will be 2, so that will come as 2 pi kf square divided by 2 pi lx times 2 pi ly times 1 by lx ly, so that gives you just a minute. Just a revision. Okay, so you know that, okay, this n is going to give you kf square upon 2 pi, so we know that basically our kf radius comes under root of 2 pi n. Now here our n is equals to, in the question it is given that what we have is a rectangular, simple rectangular primitive set, 2-dimensional matter. It has one atom of one valency. Okay, so basically we have just one electron. That means just have one electron, and our total will be 2 times, and the lx ly here, lx is equals to 2 angstrom, which is 2 into 10 to the power minus 8 centimeter, and ly is equals to 4 angstrom, this is equals to 4 into 10 to the power minus 8 centimeter. So our n is equals to, we just have one electron, lx ly, that will be our electron per centimeter square. Alright, so that will be equals to 1 upon 2 times 10 to the power minus 8 times 4 10 to the power minus 8. This will be electrons, electrons per centimeter square. So alright, so basically what we have, n is will come as 1 by 8 into 10 to the power 16 electrons per centimeter square. So your kf will be just equals to square root of 2 pi n, which if you calculate, 2 times pi 2 pi 1 by 8 and to the power 16, so it comes as 0.89 into 10 to the power 8 centimeter inverse. Alright, so this is our kf value. So here we can see that this is our kf value, and if you see our Spinning zone lengths, so Spinning zone lengths were like 1.57 and 3.14. So and this is 0.89 is a kf radius. So I guess is it we have to draw something or calculate the radius? Okay, B part just have to draw. The C part, it is asking draw this sphere to scale on a drawing of the first Spinning zone. Okay, so now we have to draw this sphere to scale on a drawing of the first Spinning zone. Okay, so whatever our drawing of the first Spinning zone, we have to draw it to scale, and make another sketch to show the first periods of the free electron band in the periodic zone scheme for both the first and the second energy bands. Assume there is a small energy gap at the zone boundaries. Okay, so So in the C part, now we have to draw our Fermi sphere. Now these are in the units are in these are in centimeter inverse, but okay, but I will just keep it like this only, not change it. Alright, so basically let's say this is our first period zone. Okay, and this is my gamma point 0. Now this we know that pi by a distance, I know this is around 1.57 into 10 to the power 8, and this point that's why I was showing this point. So this point will be 0.78 into 10 to the power 8 centimeter inverse 0. So although these are in centimeter inverse, I am gonna take this centimeter inverse as our length. Alright, so maybe somewhere some people have done a little different, but I am going to go with this. Alright, so basically this is my gamma point. I am considering this is my gamma point, and I am considering this as my length. Okay, so this length from here to here, right? This I know is I am considering 1.57 into 10 to the power 8. Okay, this is 1.57. If I have my kx and ky, let's say this is my kx, this is my ky. So this length, this is 1.57 to 10 to the power 8 centimeter inverse, and this. So I am drawing everything in the reciprocal space. Although the units are centimeter inverse, so you sometimes it's somewhere the things are changed a little bit, but I am considering it to be this length only. Okay, so we have this. Now my radius is 0.89. So I know that. So if I draw my Fermi sphere, so I know that considering this as my length units, my Fermi sphere will cross it because it is 0.89 and I have 0.78. So it will cross this one, and I will have something like this then. This will be my Fermi sphere. Alright, because the Fermi radius, this radius, this is this radius is kf equals to 0.89 10 to the power 8 centimeter inverse. Alright, so my Fermi sphere will be something like this. Okay, so this, so by scale we can draw my Fermi sphere like this. So it will go out of my first period zone. Okay, and this is my first period zone. I have drawn it again. This is my first period zone. Okay, so I hope you understand. Okay, this was my first period zone. Alright, which is up to 1.57 and 0.78. Our total length was 2 times of this animation that we have written. And my Fermi sphere will now go, because its kf is 0.89, so it will go outside along this ky direction. It will go outside. Alright, and now the other part is asked to us is make another sketch to show the first few periods of the free electron band in the periodic zone scheme for both. Okay, now I have not drawn it, but it seems like our system will remain, because it's very small, so it will be in the second periodic zone only. So we have to basically, what we have to do, we have to make another sketch to show the first few periods of the free electron band in the periodic zone scheme. So we have to bring our this Fermi surface from the second periodic zone to the first periodic zone for both the first and the second energy bands. Assume there is a small energy gap at the energy boundaries, same boundary. So we have to assume that there is small energy gap at the boundaries as well. So if we assume that when we assume some energy gap, then we know that more part goes into this first periodic zone and less part goes into the second periodic zone. Alright, so what will happen is, if we assume that, then you can check it. So what will happen if you draw it in the, for the first band, if you draw, so let me just make for the first band. Okay, so for the first band what will happen is so for the first band we will have this thing here, but it will come more into this area. So what you will have is something like this, right? We will have a circle, but then some instead of going it will be some more part will be like this. Okay, so this is the kind of stuff that we are going to get for our first band. And then it is also, I guess we have to repeat it. We have to use the periodic zone scheme as well. Okay, so and if I just repeat it, I can just repeat it like this. So I will have something like this. So then this color is not the same. Just repeat this. This will be just repeated. Alright, so this is my first band. Alright, and my second, and how the second band will look like. Second band, there will be this shape, but this will be a little distorted. So what I can draw is outside this region, outside my first region, so this will be, my surface will be a little distorted. So instead of being this, it will be some less value. Okay, and then I will just repeat this thing. I will just bring it by this periodic. Okay, I will just bring it here. Okay, and similarly I will drop. I will bring this one here. Alright, this is smaller compared to what it was there, because we have to consider some cutting, because we have to consider this thing. Even there is a small energy gap at its own boundary. Alright, so this will be my second band, and if I just repeat it, then it will be made like this. So this will be my second band. Alright, so this is your first band, and this will be given by our second band. Alright, so if you remember, this would have been a complete circle if I would have not assumed any gap, but since I am assuming any gap, it will go something like this. Okay, so I have not drawn it to the perfect, but just right, and this will be my first band. Alright, this will be your first band, and this will be your second band. Alright, so this was the problem on the Fermi surface, or a 2D element. Alright, so let's just do this another problem from Charles Kittle. So this is problem 1 from chapter 7 of Charles Kittle book. So it is regarding a square lattice and the free electron energies. So first, what we have to show for a simple square lattice, we have a two-dimensional simple square lattice, that the kinetic energy of a free electron at a corner of the first zone is higher than, the kinetic energy of a free electron at a corner of the first zone is higher than that of an electron at midpoint of a side face of the zone by a factor of root 2. Okay, so we have a square lattice, and what it's asking that, okay, if you have a square lattice and you have a reciprocal space, also you have a square lattice. Okay, the kinetic energy of a free electron at a corner of the first zone, which is your first Brillouin zone. Okay, the electron at a corner of the first zone is higher than that of an electron at the midpoint of side face of the zone by a factor. Okay, at a midpoint of a side face of the zone. Okay, midpoint at the side face of the zone. Okay, where midpoint, let's say if you have a this side, so it will be something like here. Okay, some here. Let me just write the answer first, and then we can discuss it here. Okay, now the wave vector at the corner is longer than the wave vector at the midpoint of a side by root 2. Alright, so the wave vector at the corner point. Okay, so corner point, if you have some A, then whatever the midpoint of a side, that the wave vector of the corner, it will be longer because it will be pi by E, and this is pi by root A. At the midpoint of a side will be by root 2, and as energy is directly proportional to k square for free electron, the energy is higher by root 2 whole square. Okay, so that's the reason. Okay, so we have to show that for simple square lattice, the kinetic energy of a free electron at the corner of the first zone is higher. We have to find the kinetic energy, and we know that the energy for a free electron, that is just proportional to k square, and we can see that the wave vector at the corner is going to be longer than the wave vector at the midpoint by midpoint of a side by root 2. Alright, just alright, so this is quite simple. Okay, so you can see that if you have this square lattice. Alright, so what it is saying is that you have a midpoint at one of the side. Okay, we have a simple square lattice. We have a midpoint at one of the face, which is one of the line. Alright, and then you will have a k vector at the corner as well. Alright, so here you can see that if we see in k space, let's say this distance is some a distance, then you can see that this if the length of this k vector, let's say this is k1 vector with the distance a, while this k vector distance, as you can see from the Pythagoras, if this is a and this is also will be around a, so this k2 distance will be root 2 times of a. So the k vector at a corner, it will have a magnitude root 2 times larger than the magnitude of the k at this midpoint of the face, and since the energies, they are directly proportional to the k square for a free electron, thus the energy will be also root 2 times higher, root 2 whole square times higher, which comes as 2. So that's why the kinetic energy or at this k point of the electron will be larger by 2 times compared to the electron which has the k point here. Right, so I hope this is easy understood. I should have brief explanation. Right, so if you have a square lattice, this is your corner, this is your midpoint. Alright, so this k1, let's say this is some distance, at some distance k, then this k2, your corner 1, you can see this will be root 2 times of k. Okay, you can just check for a square lattice. If this is k, this will be also k. This will, because this is at the midpoint, so this will be k, this will be k, so this will be root 2 times of k. And since this kind, for the free electron, kinetic energy is directly proportional to k square only, so the kinetic energy will be 2 times at this point. And that is what it is. The wave vector of the corner is longer than the wave vector at the midpoint. Okay, so k2 is root 2 times of k, so k2 is greater than k1 midpoint by root 2 times. Alright, and thus the energy is k square, so the energy is higher by root 2 times whole square, which is 2. Alright, so this is an easy one. Now then the B part is, what is the corresponding factor for a simple cubic lattice in 3 dimensions? Now if you think about it in 3 dimensions, then you can see that for the corner point and for a midpoint on the space, if you make it, okay, because and in that case this will come around root 3 times actually. Okay, so let me just first write it and then I will show. So in 3 dimensions, the energy at a corner is higher by root 3 whole square than at midpoint of a face. Alright, for this again you have to just draw a cube. Let's say this is my cube, right, and I will have a center here, I will have one corner here, and I will have this one length here. Let's say this will be some length k. I have to join this line here. Right, so this is in 3 dimensions. Now the length of this k vector will be from this center point. Okay, from this gamma point, 0 point, you have to take the length. Okay, from this 0 point you have to take the length. So this k1, which is at the middle, so k1, let's say k1 is some k value. Alright, and if this is k, then you can see, then we can calculate that. Okay, so for it's difficult to show it in 3D, but basically if you have this distance, this is basically, you know that the body diagonal is basically root 3 times of this total length A. Like if this box will have in k space, this box will have a length 2k, so this and this will be basically your body diagonal, so it will be root 3 times of 2k and half of that, so it will be root 3 times of this k. Alright, because this is the body diagonal. Okay, so yeah, I should have drawn it as a body diagonal. Alright, so let's say in the 3D case, 3D box in k space. Let's say this is my center origin, this is my corner, this is some point 1 at the middle of the face, let's say this one. Alright, now this there will be one k vector here and one k2 vector here. This k2 vector will be my body diagonal. Okay, so if this distance is, let's say, some 2k, this will be my k1 and this will be my Okay, basically you will have at a center, and this k vector, this will be around the body diagonal. Okay, so if this distance, this is your corner point, this is let's say my k2, and this will be your face k1. So this k1, if this distance is basically, let's say this is some 2k, your 3D distance, so k1 will be equals to some k, then k2 will be equals to this root 3 times of, this is the body diagonal, so root 3 times of this 2k half, which will be root 3 times k. Alright, so the magnitude of your k2 at the corner will be root 3 times of this. Okay, similar like in the 2D case it was root 2, in the 3D case it will be root 3 times. So I hope you understand from like this is a body diagonal, you just have to take the half, so it will be root 3 times of this. And 2k will be just 2k divided by 2, which is k. Right? Alright, so hopefully this is understood. So in 3 dimension, the kinetic energy will be just 3 times compared to the whatever the kinetic energy is at the midpoint of the phase. Okay, because we are talking about free electron case only. Okay, now the C part is what bearing might the result of B have on the conductivity of divalent metals. Okay, so what happens because of this B case? So basically B case, what we have seen is that if the electrons are at the midpoint of your this three simple cubic lattice, then it will have the kinetic energy at the corner will be 3 times than at that midpoint of phase. So what it is asking us what happens in what effect that thing has on the conductivity of the divalent metals. So for this, okay. Unless the band gap at the midpoint of a phase is larger than the kinetic energy difference between this point and a corner, the electrons will spill over into the second zone in preference to filling up the corner states in the first zone. So divalent elements under these conditions will be metals, not insulators. Alright, so what we are saying is that because of this B condition, where you can see that the kinetic energy at the corner will be 3 times than of the electron will be 3 times than at any of the midpoint. So unless the band gap at the midpoint of a phase is larger than the kinetic energy difference, whatever kinetic energy difference is between this point and the corner, the electrons will spill over into the second zone in preference to, what will happen? The electron will if the band gap is not larger than this kinetic energy difference, then what will happen? The electron will spill over into the second zone in preference to filling up the corner states in the first zone. Okay. Because the kinetic energy on the corner is quite high, so the in preference to that, it will start filling up into the spill over into the second zone, and because of this diamond elements, if the band gap is not large enough, then this will be matters, not insulators, under these conditions. Alright. So this was our problem number 6. We are just left with last 10 or 12 minutes. So in the last 10-12 minutes, we are just gonna go through the assignment problems once. Okay, we just discuss them quickly. Alright, so these are for the assignment number 5. The problems were done. So the first problem was in the case, okay. Now, in case of electrons in a weak periodic potential, okay, so we are talking about electrons in a weak periodic potential, energy is equals to free electron energy near the Brillouin zone boundary. So that is not true. Okay, so we know that, okay, from the weak periodic potential, the effects will be at your Brillouin zone boundary only, and away from the Brillouin zone boundary, it will be similar to your free electron gas. So this will be wrong. Then energy is equals to free electron energy away from the Brillouin zone boundary. That is true. Energy values are continuous. No, we have a band. We will see some gaps around the Brillouin zone boundary. We are considering weak periodic potential, and another option mentioned. So that is not option, and this is option number B. And the explanation is also given the same. The free electron approximation remains a good approximation, well away from the edges of the Brillouin zone. Wave vectors close to multiple of pi by a are mixed together and have their energies altered by their periodic potential, as you have seen in the lectures and the codes as well. Right. Now the second part is consider two wave functions cos pi x by a and sin pi x by a, where A is a lattice parameter of a 1D lattice. Which of the following statement is true? Both the wave functions have the same kinetic energy. So for the kinetic energy, you just have to manage h square by 2m d square psi by dx square. That is, you just have to take the double derivative, and we can see that both of them will give you the same kinetic energy. Right. So both the wave function have the same kinetic energy. Because of the periodic potential, both wave function have and the explanation is also given that because of the periodic potential, both wave function have the same energy, and you can calculate it as well. Now both the wave function have the same potential energy. That has been checked. That is not true if you go to the lecture. So one will have a plus u and one will have a minus u, which relate to your band gap. Now both the wave function have same kinetic and potential energy. No, both the wave function have the same potential energy, but different condition. No, they will have the same kinetic energy. Alright. Now in the reduced zone scheme, third problem is in the reduced zone scheme, all the bands are plotted in all the. We can do it del square by del square cos sin cos. Okay, yeah. You can take the expectation value of kinetic energy as well. To check it, you can take the expectation value for the cos function. So basically, that will be your sin. That will be basically your cos pi x by a. Let me just do this calculation quickly. So to check they have the same kinetic energy as has been done in the class as well. So the explanation is given that you can they will have the periodic potential, both wave function have the same energy, or you can actually do the expectation value of the kinetic energy with respect to, let's say, function 1. So that will be equals to, if you do an integral, okay, and it will be from x will be from 0 to a, you have cos pi x by a. I am not taking minus h square by 2m, that constant, d square by del x square of cos pi x by a dx. So if you do a double integral, then you will have pi by a, and let's say some constant we are ignoring. We can ignore that, and then will be cos differentiation will be sin differentiation will be cos will be minus sin, sin will be cos, will have a minus sign. Minus I will have minus some negative value from 0 to a, cos pi x by a and sin pi x by a. Okay, and this you can integrate. Okay, cost, there will be some cos 2 pi x pi. So this will be for the kinetic energy 1. Similarly, you can do the we can do the same expectation value for the kinetic energy 2 part as well. We just have a sin pi x pi a. We will have a cos pi x pi a. There will be cos square theta. You can check basically. We don't have touch time, so I'm not really. Here you can do the expectation value as has been done in the lecture as well. You can calculate the expectation value of the kinetic energy for both the wave function, and you will find that the expectation value of this kinetic energies will also going to come same. All right. I don't have time for. We are already. We just have to discuss this assignment quickly. Okay, but you can check the expectation values as well. They will also come the same. Now in reduced zone scheme, all the bands are plotted on all the brilliant zones. That's not true. In reduced zone schemes, basically you plot all your bands within your first brilliant zone. So that's not true. The first and second band is plotted in the first and second brilliant zone respectively. No, all the bands are plotted in the first brilliant zone. C option is correct. Reduced zone scheme contains all the information in the first brilliant zone. The fourth option is identify the correct statements. An X-ray is black refracted when its wave vector lies on a black plane. That's true. And then in a crystal, black scattering of X-ray and electron follow different principle. No, they follow the same principle. In a crystal, X-ray diffraction is possible, but electron diffraction is not. No, a block electron is black refracted when Laue condition is satisfied, as you seen in the lecture. That is why we are drawing the bisector symbol for the plane zone. Okay, so block electron black refraction Laue condition is satisfied when we have a black refraction. Okay, now for a pure semiconductor, it will be an insulator at t equals to 0. It's not a matter at t equals to 0. It has a partially filled band at t greater than 0, and it has partially no. Okay, so it's A and C option, because if you increase the temperature, if the band gap is small, then some electrons will go from your lower bands to upper bands for t greater than 0, and then you will have a partially filled bands. Electrons in the valence band do not have sufficient energy to jump to the conduction band, and hence semiconductor here as an insulator at t equals 0 gather, while for greater they have the energy and they can move on to the next band, and you will have a partially filled band. Okay, now we have to consider first brilliant zone of a 2D square lattice. How many high symmetry points excluding the gamma point are there? Okay, now for a 2D square lattice, if you remember, for a 2D square lattice, let's say if I have a square lattice and this is my gamma point, then this point, then I guess since this is a square one, so this x, so I just need to take this one point, I have to call it some x. This is my gamma point, gamma xm, and the y point will have the same plot as you have done for the, because this is a square point. Okay, so x and y point will be the same. So this will be your irreducible brilliant zone. So you just need these 3 points only. So other than the gamma point, there will be just 2 points, x and m. So answer should be B. Now if you consider first brilliant zone for a 2D rectangular lattice, how many high symmetry points excluding the gamma point are there? So in rectangular lattice, you will have this kind of a rectangular lattice. Now I will have a gamma point, I will have this x. Now since it is a rectangular lattice, so there will be anisotropy. So this x and y points, earlier this x and y was same, so we don't need to consider that y into the high symmetry points. But now we have to consider this as our high symmetry. Our high symmetry points will be now 4, because x and y are not going to be the same. So how many high symmetry points excluding the gamma point? Excluding the gamma point, there will be 1, 2, 3 points. So answer should be 3. Alright. Now consider again the first brilliant zone of a 3D simple cubic lattice. How many high symmetry points are there? Now again for the 3D simple cubic lattice, you can just check it yourself. Okay. So we can see that if I have a gamma point, then again I will have something similar thing. I will have some x point there. Okay. I don't need to go to the some at other point. There will be one corner point that I need to take care of. Alright. there will be one at this phase center as well. Okay, so you can just check that otherwise, and all the other points I can take, they will be more or less same. So other than this gamma point, there will be 3 points, and you can go to your lecture notes and you can see more about it. But basically, you can see that if you just think about cubic, so there will be one in the x. If you go in any other direction, that's the same. So you don't need to take any other point. If you go here, then you can go to any other direction. That is, you don't need to every other point. All these points like this. Let me just use 3 different colors. Okay, that's for the 3D. For the 3D part, alright, okay, so for the 3D part, okay, for the 3D part, you can see that, okay, let me just draw it. Let's say you have your gamma point here, okay, then you can have okay, so we have this gamma point here, so you can have one x point here. Okay, let's say this is your x point. Then similarly you can have your m point here, alright, and there will be one side. Okay, again I'm just doing the same thing. So, okay, let's just make okay, you have your 3D box here, simple cubic. At the center you have your gamma point, then one point will be your in the x direction, so this will be your x point, then other point will be in here, let's say your m point, and another point will be your r point, which is the one of the center of the, so one at the corner, one at the face center, you can call it x, and one at the midpoint of your h. Okay, and since it is a simple cubic, all other points, if you take anywhere, they will be the similar. So we just need the 3 points other than your gamma point, so there will be 1 to x, m, and r, 3 points. So these are the high symmetry points. Alright, okay. Then consider first reason of a 3D face centered cubic lattice. How many high symmetry points are there? Now for a face centered cubic lattice, okay, like if you are going to have a face centered cubic lattice, then you have to draw this. So your reciprocal lattice will be a body centered cubic lattice. Alright. So for that there will be different. So for the for the face centered cubic lattice, I will just show you lecture notes. So in the lecture notes it's given, you can see here that these will be your high symmetry points. So there will be, other than gamma, there will be 1, 2, 3, 4 of them. Okay, so okay, 5 of them. Sorry. Yeah, 1, 2, 3, 4, 5. Yeah, we have L, U, X, W, K. So that I couldn't draw. So like for face centered cubic, it is like, yeah, you have to remember. Sorry about that. I couldn't draw it here. But this, even if you don't remember, actually simple cubic, rectangular cubic, you can just draw it yourself. So simple it is. And maybe if you make a cuboid, then you know that you might need some x and y and other stuff as well. Right? And then the last question, like this is a small question here. Now in the energy gap, there exists no solution of the wave equation. So no, there exists solution, but that I have an imaginary complex value of the wave vector. Okay, there exists solutions of the wave functions equation with complex value of the wave vector. Okay, so this you should remember from the lecture. Then we have a solid with n primitive unit cell. How many orbits are there in each element? That will be 2n. Alright, it's a direct question. Now gap between two energy levels within a band it is typically very small because here n is at about 23 electrons, so it is very, the gap is between, if you remember, because n is 10 to the power 23, that's why this gap will be very small, 10 to the minus 22 electron volt. Now identify suitable function that fits the band structure of nearly free electrons. Now since we are talking about nearly free electrons, that's why the option will be minus 2 times cos k, because we need some gap there at the green zone. So this you can check. Then assume a 1D lattice. Okay, I guess how many questions? Okay, let's just complete. We are already out of time. So just complete it. Okay. Assume a 1D lattice with a distance between this 2k whole square, that will for the free energies only. Okay, then free electron model only, nearly free electron will be C minus 2 cos k. Now assume a 1D lattice with the distance between two lattice points equals to A. Identify the Brillouin zone boundaries. So for the Brillouin zone boundary, we know that if it is A, so then as we have drawn here, this will be 2 pi by A, and between minus 2 pi by A will be your lattice vectors, and then you will have your perpendicular bisector for the 1D, and you have a pi by A and minus pi by A. So this will be your boundaries. And under the Brillouin zone boundaries, so will be pi by A and minus pi by A. So it will be B option. And it is asking so these are the first Brillouin zone boundaries. Okay, so you can directly take B, but again we can have the second Brillouin zone as well. Okay, so it could be like we can, okay, so let me just draw a 1D lattice here. So if I have this 1D lattice, this is our ground 0 point. I will have 2 pi by A here. I will have then a 4 pi by A here. I will have a minus 2 pi by A here. I will have a minus 4 pi by A here. Now for the first Brillouin zone, you draw your perpendicular bisectors, and they will cut at pi by A and minus pi by A. Then going to the second Brillouin zone, you will join this 0 with this 4 pi by A. So we will take the perpendicular bisector between these two, which will be this one actually, which will be this one. So this will also be our Brillouin zone boundaries. This will be for the second Brillouin zone. Okay, so this green one will be for, this will be for the first Brillouin zone. This blue one will be for the second Brillouin zone. Alright, from 0 pi by A. So and then and we know that, okay, so and basically all the Brillouin zone boundary will be multiples of each other. So it will be minus pi by A, minus 2 pi by A. Similarly, the next will be minus 3 pi by A. The next will be, if you draw, so it will become something here. It will be minus 3 pi by A, and so on. Okay, I'm not drawing it. It will be 3 pi by A. Alright, so they will be multiples of this first Brillouin zone boundaries, which are pi by A and minus pi by A. So using this, you can see that it will not be 4 pi by 5A, it will be pi by A. It will be minus 2 pi by A, it will not be minus 2 pi by 3A. So the option will be B and C. Sorry. Now last problem, assume a 1D lattice with distance between two adjacent lattice points equals to A. Identify the cluster limit. The length of the first Brillouin zone is 2 pi by. So here we can see that the length of the first Brillouin zone, as we drawn here, it is from minus pi by A to pi by A, so it is 2 pi by A. So that is correct. Length of the second Brillouin zone, so that we know that the second Brillouin zone length, that will also be from minus pi by A to pi by A. So it's for the second Brillouin zone. Okay, this length will be equal to, this is pi by A, this is pi by A. So length of the second Brillouin zone is actually 2 pi by A. So it is not 4 pi by A. And length of the third Brillouin zone, again, if you go this distance, and you can check, this distance will be pi by, from minus 2 pi by to 3 pi by, and this will be pi by. Okay, this is my second, and this is my third for the third Brillouin zone. So the third Brillouin zone also, the length is coming pi by plus pi by equals to 2 pi by. So this is also wrong. The length of every Brillouin zone is 2 pi by. That is correct. The length of all the Brillouin zone will be 2 pi by. And here we have done for the 1D case, we have directly seen it as well. Okay, first Brillouin zone is 2 pi by, then it is pi by plus pi by, 2 pi by for second Brillouin zone, and for the third Brillouin zone also it is 2 pi by. So as the area of each Brillouin zone is same, the results in the is the same length of 2 pi by also be the same, and we have shown it here as well. Right. So just stop sharing. Alright, so this is so we are at the end of today's session. Alright, so in today's sessions what we did was we first completed our from the previous session we completed this that coding part. We looked at the remaining lecture 3 codes. Then we look at the coding problems from the previous assignments. Then we did some problems from Kittle. We did some problems on Brilliant Zone, a problem on Brilliant Zone, a problem on Fermi surface, and then we also did an interesting problem from chapter 7 of Kittle. And then we briefly went through the week 5 assignment solution as well. Right? Thank you for your time.